Everybody doing? I hope you're doing fine. Hope you're doing better than me. Today we have an exciting day of physics. If I can get all these things set up here. Uh, Today we're going to have Mr. Al-Khalili again. Some people complain, they say, Bill, you're spending too much time on Jim Al-Khalili. No, you got it wrong. I'm spending time on the subject matters. Al-Khalili is not the subject matter. He has done many videos on different subjects, and I'm covering the subjects. So please stay tuned to the subjects. You'll be okay. You won't get hurt. Okay. And today we have the subject of time. What is time? Anybody know? Well, if you do, please let me know, because all these mathematicians, none of them know what time is. And hopefully Mr. Al-Khalili today is going to tell us what time is. Okay, so let's get started here, and I'll be answering questions at the end, by the way, once again. Here's Mr. Al-Khalili, and he says that the following. This is how he starts his presentation, his dissertation. He says, philosophers, scientists, theologians have all pondered the meaning of time. Good, I'm glad. What have they come up with after, 2,000 years? Does time flow? Is time static? And we move through it. Is time cyclic? Can you change the rate of time? Well, if time was a physical object, yes, we could do a lot of that stuff. If it was like a stone, yeah, we could do a lot of this stuff. We could stretch it. We could make it go faster. You can do all that with a rock, maybe with an elastic band. You can do it even with air, a gas or whatever. Can you do it with a concept? Can you stretch a concept? Can you make a concept go faster? So it would be interesting, or it would be nice if Mr. Al-Khalili would begin his presentation by defining the word time, so we know what the subject matter is, And I looked. I didn't find it. Okay, so I'm sorry to tell you, he had no definition of time. So I had to look it up. I had to go to the Wikipedia, one source at least, right? All these sources essentially said the same thing. So I'm going to put the wiki's version here. Here it is. This is what the wiki says. It says, time is indefinite continued progress of existence and events that occur in an apparently irreversible succession from the past through the present into the future. Okay, so I look up the word past, which was underlined on the Wikipedia. I see, okay, what does the past mean? What does that word mean? The past is a set of all events that occurred before a given point in time. The present, or here and now, is the time that is associated with the events perceived directly and in the first time, not as recollection perceived more than once or speculation predicted hypothesis uncertain. And the future was defined as is the time after the present. Its arrival is considered inevitable due to the existence of time and the laws of physics. So we have all these words, and they're all synonym. One references the other one. So that's not very helpful. They're all, it's like we're rolling around in a circle here. But I liked one of the statements in the wiki. It says, defining it in a manner applicable to all fields without circularity has consistently eluded the scholars. So what's the conclusion? The conclusion is we have no definition of time after 2,500 years, since the Greeks, at least, I would say, that they talked about time on and off, right? And here we are 2,500 years later, we don't have a definition of time. Nobody has any idea what time is all about. And yet everybody talks about time as if they were experts. And, the last statement there, the operational definition of time, just in case, right, does not address what the fundamental nature of it is. Yeah, it'd be nice if someone told us what they mean by the word time, And how can you give a dissertation on time and not know what time is? And so I had to put a definition there, okay, so that people know what time is, not because I use it, because like I'll say there, I don't want to get ahead of myself. Time is exclusively a mathematical parameter. Okay, that has nothing to do with physics. Okay, we have no use for time in physics. In physics, we must explain, and time is a description. Specifically, when we quantify, it's a mathematical description. Okay, definition of time. Here it is from the horse's mouth, from me. Okay, time, a comparison of two motions. What is time? You're comparing two motions, and you have to use one important ingredient, which is memory. You can't have time without memory. Okay, so do rocks understand that? No, rocks do not understand because rocks do not have memory. So rocks do not understand time. Okay, I hope you grasp that. Yeah, it's only living things that conceptualize time, that can conceptualize time. Plants, do they conceptualize time? I don't think they have memory. They have a different type of cell. They don't have like the neurons that we have, so I don't think they conceptualize time. How about animals? Well, some animals I think have an idea of what time is. Like, you have the lion, and the lion waits for the migration of the herds, whatever they hunt out there, buffalo, zebras, they go through this cycle. And when they come back, they say, oh, it's time for hunting again. It's that time of the year. So I think they have a notion, maybe not of hourly time, seconds, that kind of thing. That's not so important for them, but they probably have a calendar notion in their heads. There's a cycle, yearly cycle. Okay, so they probably have an understanding or an intuitive understanding of the seasons. Okay, hello. So time, a comparison of two motions. You need to compare two motions in order to conceptualize time. And no one has figured that out in the last 2,500 years. Absolutely outrageous. Time is not a physical medium, therefore can't travel through time. So if you try to travel through time, well, you can try to travel through love, through spirits, then you can travel through them. But if there's no such monsters, if they're all concepts, well, you can't travel through a concept. And that's the problem with time. It's irrational to say that you can travel through or through time, like back in time or forward in time. You can't travel in time or through time. Time is not a medium. You can travel through molasses, you can travel through air, you can travel through water. You can't travel through concepts. And that's absolutely important to understand. And it's not semantics. We're talking about real stuff here. You can't travel through nothing. And concepts are nothing. Okay? Okay, here's a pictorial version of my definition of time. Okay, here it is. You have motion, two or more locations. Okay? And time is two motions plus memory. Okay? So what's the difference? Well, you move by definition. When you look at the moon, you say, well, is the moon moving? Well, what are you saying? You're saying if the moon occupies two or more locations, it moves by definition. Okay? On the other hand, time is a little different. You have to compare two motions, for otherwise you have no time. All you have is motion. Okay, when you compare two motions, and that means you have to remember, you have to memorize the previous motion, either through some device or through your own brain, and only then can you compare these two motions, because you have to remember the previous motions as well. Okay, so and of the other object. So there it is, in a nutshell: motion versus time, two different things. They're not the same. Time requires memory and two motions, whereas motion requires two locations. Okay, I hope that's clear. Not everybody grasps that. It takes a while maybe to wrap your brain around it. Okay. Okay, how does Al-Khalili continue? Well, he says the following. He says, most of us have this picture of time, which was explained by people like Newton, right? That time is somehow separate from space. Well, hopefully they're separate because, they're not objects, neither space nor time. Space is nothing, that which has no shape. And a concept is a word that invokes or embodies two objects or two words that are treated as objects. One of them usually is space. So yeah, I don't know how they when we talk about separate. Are we talking about physical separateness or ordinary speech conceptual separateness? See, when we talk about physics, we have to treat the word separate or separate, right? In physical terms, you can separate two objects, then they're separate, okay? But you cannot say you're going to separate two concepts. You separate, I don't know, love from hate. You separate them. What did you separate? I mean, that's great for poetry, for ordinary speech. You can't use that language in physics. And people don't always grasp something as basic as that, unfortunately. Space, the universe. He thought space and the universe are the same thing. And they're not. Universe includes matter. Space does not. Okay? The word. Space, that which has no shape. Universe, space, and matter. So they're not the same thing, universe and space. People treat them as synonyms many times because they're really, when they talk about universe, they're thinking of that infinite space. That's the notion they have going through their brains, okay? Space, the universe, is a stage on which we all act out our lives and the events that take place. And time is this cosmic clock that ticks by the seconds, the minutes, the hours at the same rate everywhere in the universe. That was Newton's notion, okay? And a lot of people have that notion, okay? And he says, Einstein came up with something different. He comes along and says that picture of time is wrong. That picture of time is wrong. Time doesn't flow at the same rate for everyone. You can change time, you can slow it down, you can speed it up. How can you change speed and slow down time if time is not a physical object? You can do that to a rock, no doubt about that. You can slow a rock down, maybe throw it through molasses, it'll go slower than through water or through air, I would think, right? Same force behind it, etc., right? So how can you speed up or slow down a concept? And you would say, well, Bill, you're taking this out of context. You're harping too much on semantics. These guys are going to treat time as a physical object throughout their presentation. All of them do. So it's not that I'm picking on them. It's that they have no other language. This is the language they use. Why? Because they're turning this mathematical concept called time and they want to introduce it into physics. This is the reason. And you say, well, why would they want to do that? Well, it's because they have time in their equations. And they don't have the word time in there. They have 1 second, one year. They have some number in there with a unit, and they have to do something with that. That's why. And if that has no meaning other than in mathematics, then it's worthless, okay? So they have to make it real. They have to introduce it into the real world of physics, and they say, oh, we can tell you something about the real world with this little thingy we call time. And for that, they have to convert time into a physical object. That's how time metamorphs into a shape of some kind, because now you're going to distort it, you're going to make it go faster, you're going to do all these things to time. For that, you got to have an object. And so they have to turn time into an object. And when you point that out to them, they say, well, hey, you're not supposed to take it literally. Make up your mind. Are you going to introduce it into physics and we take it literally, or are you just going to keep it in mathematics? That's where the problem is, okay? Okay, so Einstein says that you can speed up, slow down, and this is what these people like Al-Khalili, this is what they learn in college by rote. And they say, oh, okay, drooling. So they take it as law because the teacher's teaching them. They never questioned it. Okay. And here's another fellow, colleague of Al-Khalili, died a couple years ago, Mr. Hawking. He wrote a book, A Brief History of Time. And what did he say? The concept of time. Concept, that means it's not a physical object. Okay? The concept of time has no meaning before the beginning of the universe. Okay, assuming there was a beginning of the universe, he's saying before that there was no time. So what does he mean by time? Well, you go throughout his whole book, and he's got a glossary at the end of the book. You will not find a definition of the word time. He's talking about a brief history of time. His whole book is about time, almost 200 pages. You will not find the word time defined anywhere in there. Just in case, Paul Davies, another fellow, Australian, I think he is, he defined, he wrote a book about time. I mean, you know, again, about time, what is he going to talk about? He's going to talk about time, okay? And nowhere in his book will you find a definition of the word time. So none of these people define time, but they give all these lengthy dissertations on the word time. They're experts at time, but none of them define it. And so what does Hawking say? This was first pointed out by St. Augustine when asked, what did God do before he created the universe? Augustine didn't reply. He was preparing hell for people who asked such questions. No, instead he said that time was a property of the universe that God created, and that time did not exist before the beginning of the universe. Exist? I thought only objects could exist in physics. So now concepts exist, love exists, information exists. You see why we have to define the word exist? Because they're saying that time exists. In physics, we can only use the word exist in relation or in the context of objects. That means concepts cannot be said to exist in physics. This guy is saying not only that they exist without defining exist, but he's saying that time, which is a concept, exists even though time has not been defined. He has not defined time either. So we don't have a definition of time. We don't have a definition of exist, but time exists. You see where the problem is? And yeah, it is. It's not just semantics. It's that these people are getting away with murder by saying all this nonsense that, you know, that they haven't justified. They have not prepared the groundwork, the foundations to say these statements, to make these statements. Okay? So it's a property of the universe, whatever that means. You know, maybe it's a property of humans. You ever think of that? I mean, you know, what are we saying here? Property of the universe. Well, the universe is matter in space. Where's this property called time in that picture? You know, I don't see how time fits into, which requires memory, which is a comparison of two motions. I don't see where time fits into the universe. I mean, let's erase all living entities from the universe. God comes in with his magic wand, wipes every living entity, including plants, just in case. Wipes everything out that's alive, that's moving against gravity. That's life, right? And do we have time? We have the universe. We have space. We have matter, all the atoms, all the asteroids, planets, stars, galaxies. Where's time? Where's the memory necessary to ponder, conceptualize time? So yeah, this is the issue. The issue, these people get away with murder because they do not justify the statements that they make. They just make broad statements saying, oh, you understand, don't you? Yeah, yeah, I understand quite a bit. Okay, where does Al-Khalili continue then after that? Well, he says something even more disastrous. He says, now, I don't mean psychological time. We know that this is not time speeding up and slowing down, you know, like the watch, like if you got a bad watch, okay? And you say, oh, it's ahead of its schedule. It's not 4:05, it's just 4 o'clock. So my watch is running fast. That's not what he's talking about. That, like he says, you got to go and fix your watch when you got that. He's talking about something else. He's saying, this is your subjective impression of the rate of flow of time. Einstein said, no, time really can speed up. and or slow down, and there are two ways of doing this. Okay, I want to know how to speed time up. Really, I want to slow it down. I don't want to age too fast. I'm getting up there, I'm going on 68 this year. If you were to travel close to the speed of light, then your time would be seen to run slower than if you were not moving. Oh, man, Jesus, then I better move fast, right? So then I don't age. But it turns out that when I run fast, I lose so much energy that I think I'm aging fast. So if I strap a clock to a rocket and have the rocket fly past me at close to the speed of light, I will see the second hand on that clock ticking more slowly than an identical clock here on Earth. Okay? This is not an optical illusion. This is not, this is real, okay? Time really would slow down. What is strange is that if I were on board that rocket, I would see Earth's clock running slower. So who's running slower? If I see you running fast and I go past you and you see me running fast, or vice versa, what have we learned here? We learned that this is an optical illusion based on the observer. He's saying it there. Because if I see you running slow or fast and you see me exactly the same way, running slow or fast, that means it's all just our impressions, our personal opinions. It's just subjective. Okay? And if it's subjective, what does it have to do with physics? See, what these people are going to try to sell you is that, no, this is real because we measured it and we've proven it and I don't know what else, And so they tell you this is real, meaning that when you travel close to the speed of light, you're actually slowing down time. That the watch that you're carrying with you runs slower simply because of how fast you're going. Okay, this is what they're saying. Okay, keep an eye. That's the crux of the problem. Okay. Okay. Oh, sorry. Hang on. Got the wrong one here. Let's get the right one. Okay, so Al-Khalili continues here. He says, in order to explain, I like this part, he can't convince you, so he's going to try to convince you through authority, okay? In order to explain this in a way that I can get you all to believe me will take longer than this session. Ah, shucks. And I sort of have to hope that you would trust me. So I have to trust. I think this is the problem. This is a great part of the problem. He goes to college, right? And he trusts the advisor, the PhD advisor, or his instructor, his teacher, whoever. He trusts them. Okay? But he says, you have to study relativity. Yeah, I guess if you brainwash yourself with relativity, yeah, eventually you're going to believe, right? It's like reading the Bible. Eventually it sinks in, right? I teach relativity to my students, and it's really by lecture 10 or 11 that the penny drops and they say, I see, yes. Especially when you threaten them with having no career. Oh, I see, I get your point now, because you have to go through various steps of explaining the ideas. In other words, they can't point to it, they can't show you immediately, they have to go through this process of indoctrinating you and see if you fall in. And if you don't fall in, well, maybe you're too intelligent, and they say, well, maybe physics is not the right career path for you. You know what I mean? You're never going to make it. And for sure, we're not going to recommend you to any, think tank. So that's how they weed people out. Okay, so he has to move on to have some proof for this. And he doesn't have really proof, but he gives the famous example of the twin paradox. Okay, and here it is. We have the Einstein brothers, okay, twin brothers, and one goes out into space, comes back. When he comes back, his brother looks like his grandfather. Well, the guy who traveled through space, Frankie, he doesn't age a minute. Okay. Good for women. A lot of women would love that. They say, hey, take me to space so that I can find the fountain of youth, go back in time. What it tells us is that if you travel very fast, you can travel into the future. Unbelievable. grown men, people who study at the university say such nonsense. I mean, forget about the traditional religions. They come from way back when, and all these people had ghosts and spirits and gods and angels. Okay, fine. It came from our forefathers. A lot of people today believe in all that stuff. Why? Because they say, well, it's tradition. I went to church, and when I was a kid, my father's indoctrinated. Okay, fine. But a guy who goes to the university, supposedly is a thinking individual, has a lot of, I mean, if he's there, he's got at a high level, like a PhD level, he's got to have some intelligence. He has to be able to think for himself, you would think, right? And it says, what it tells us, this is what he says, after going 10 years to the university plus, a few more years doing professional work and teaching and so on. What it tells us is that if you travel very fast, you can travel into the future. The famous example is the twin paradox. Alice, 1 year, Bob, 10 years. Okay, so he's going to make that comparison where Alice just goes into outer space, comes back, she travels close to the speed of light. When she comes back, Bob has aged 10 years and she's only aged 1 year. She has time traveled 9 years into the future. If she could travel closer to the speed of light, she could travel for half an hour and come back 1,000 years into the future. Oh, these are great calculations, like on paper, if you want to toy around with equations and so on. Yeah, this is fine. I've got a little example here. Let's see if I can find it here. There it is. This is what they're saying essentially. Okay, listen to this. They're treating the dimensions as physical objects, as tunnels. Like I can go through the dimension of width or height, okay, which really is not a dimension. If I can travel, it's a vector. Vectors have to do with motion. Dimensions have to do with orientation and tilt and how an observer perceives an object, or how the object faces and points in three mutually perpendicular directions. That's what dimensions have to do with. What is a vector? Vector is how it can move in mutually perpendicular dimensions, okay? But they go in there and they use the word dimension. They talk about breadth, which is a vector, and they ask you to go through this little one-dimensional tunnel. One-dimensional, is it because it only has one dimension? No, it's because you run. Because again, they're talking about a vector. They're talking about a line that represents motion. That's why it's one-dimensional. So they're not talking about a physical size or anything of that nature. What they're talking about is one-dimensional motion, meaning they're talking about vectors, meaning they're talking about breadth and not about dimensions, not about width. Okay? But they have never established the difference between vectors and dimensions, because in mathematical physics they don't use either. What they use are number lines, okay? So here it is, okay? So we're going to travel through a dimension for the first time in your life, okay? So here it is, okay? So this is how they do it. Well, they have this equation, and the observer, the time he measures for the astronaut, okay, is according to that equation. Let's get it started here, okay? We turn these two really number lines, they're not even coordinates, okay? And they turn this into time and space, and you see that number there is changing 0.95, 0.98, 0.99. They play around with that, and by playing around with that number, it just makes the astronaut go faster. That's all it does, okay, along the time dimension. And because he goes faster, right, his time, the atomic clock on his spaceship measures time slower. That's their argument. But these people are talking about, moving through a time dimension. They're saying you're moving forward, you're penetrating time, if you can even conceptualize such a monster. So they're saying you're moving through time, okay? And not through space, okay? And so because you move through time, the person, the observer on Earth, okay, he uses this little equation coming up here in a second here. He uses this equation, And he measures, see, the astronaut measures his local time, whatever he measures on board. The observer measures something from very far away, and he says, oh, my time is tremendous. I've gone 50 years. Whereas the astronaut says, hey, only a few minutes have gone by in my clock. Essentially, that's what it is. It's the, what is it, the Lorentz factor that they use to calculate this, and that's what's inside the square root there on the bottom as a denominator. And so what they do is they use this and they calculate. The question is whether any of this has to do anything at all with reality. Is this what happens to a human? Will a human go out into space? Will a twin brother go out into space, come back and find his brother looks more like his grandfather? Does this make sense? Two people come out of the same womb, essentially at the same time, a few seconds, maybe a couple minutes apart, and one is 50 years older than the other. Well, the way we do it in science is very simple. Very simple, okay? We throw all atomic clocks away, and we throw them away because according to special relativity, okay, time dilates. No clock that you take on board the, your spaceship can measure time accurately, because as soon as you speed up to close to the speed of light, according to special relativity, time is going to dilate on that clock. So you can't trust that clock because it's going to dilate. And the one left on Earth, well, that's going around with the Earth. So how accurate is that clock? Which clock should we take as the standard? Which one is the correct one? Well, you can't. You just say one clock is going slow, the other one's going fast. That's all we're saying. But we don't know which clock is right. So the way we do it in science, in real science, in genuine science, is we say, well, what is the definition of a year? And a year is one revolution of the Earth around the sun. So if you want to know when the astronaut, when Frankeinstein comes back and meets his brother Al, the only way we're going to find out how many years went by is not through their atomic clocks. We're going to find out how many revolutions the Earth made around the sun. And so let's say, I don't know, 20 years went by. Well, I don't care what their clocks measure. Whatever their clocks measure is irrelevant, because aside from the fact that we do not count, how many years you are, or how many candles to put on the cake by counting seconds, because my cake would be full of candles. No, the way we do it is we count years. And so in my case, I would have 68 candles, or more likely they would just put a 68 there, number. They would put a 68. And that's how many times the Earth went around the sun since I was born. Period. We're done. And so when the flying astronaut comes back, Frankie, he comes back, meets his brother Al on Earth. All we have to do is find out how many times the Earth went around the sun, and that had better be a fixed number. It's either 20, it's 25, it's 30, 35. It can't be for this guy 50 years and for this guy 1 year. You see what I'm saying? The number of times, the number of orbits of the Earth around the sun is fixed for everyone in the universe. I don't care where they are, even for God. So when God comes back to Earth, he can't say, well, for me, time dilated. I don't give a damn, God. Here the Earth went around the sun 10 times. I'm sorry. You got to take our word for it. We don't care about your atomic clock. Okay, we don't measure years with atomic clocks. Okay, so how did they figure this out? How did Einstein come up with all this nonsense? Well, he did it with a thought experiment. Did it a couple of them. One was with a train. That was, I remember he did this in like 1905. So they had these choo-choo trains, steam trains still. Okay, and so Einstein said, well, what if I was on a train? Well, I would see, a lightning bolt hit simultaneously, right? The front of the train and the back of the train at the same time if I were an observer on the platform. But if I'm on the train, since I'm moving in the direction of, the front of the train, right, I would see that lightning bolt come to my eye faster than the one from behind, because I'm moving in that direction. Okay? So this was Einstein's reasoning. And here it is, just so you can see it. Here's the train going through. The guy on the platform, he sees both of those strike his eyes at the same time. You know, the lightning hits the front and the back at the same time. Let's assume it's the same bolt, okay? Just hits front and back right at that moment in time. The waves or photons or whatever you want to consider, they hit the observer on the platform, his eyes. They hit him at the same time, okay? And that's a little different than what the passenger would note. The guy who's on the train watching through the window, he would see something different. He would see the front hit before the one on the back, only because the train is moving in the direction of the front, okay? So the light from the front should travel to his eyes faster because he's shortening the distance in front of him and extending the distance behind him. Does that make sense? Okay. So that's where Einstein got the idea. Okay. And what argument do I have against this? Well, Einstein essentially was talking about observers. And the first thing we do in science is we kill the observers. We do it mafia style. We wipe out the observer, no witnesses, okay, no testimonies. We wipe them out. We don't care what they thought they saw. Maybe they were on drugs and they saw something that they shouldn't have seen. I don't know, with a devil coming together with a lightning bolt. You know, we don't care about any of that. We care about objectivity. And the way we get objectivity in the universe, we kill all life in the universe, in every planet, wherever they are. No more life on Earth, in the universe. That's how we start. So now that we have no life, okay, now we can objectively understand whether, you know, light struck a given point simultaneously or one point before another. Okay, that's what we're going to compare. And to do this, what I'm going to do is I'm going to put Einstein in an electric chair. Okay, I'll put Einstein in an electric chair, and that electric chair is going to be tied to the railroad tracks. Okay, you follow me? We have an electric chair, Einstein sitting in it, you know, with all the devices, all the casts, all the things. We're going to electrocute Einstein here. They should have done that a long time ago. And we're going to have two wires, equidistant, perfectly measured, right? From the front of the track and the back of the track, right at the point where, for the exact length of the train with its, you know, wagons. Okay? So that when the front of the train touches a little device, the back of the train touches another device exactly at the same time, and those two lightning bolts, those two electricity shocks, you know, all those two currents come to the electric chair at the same time. If they come at the same time, there's enough electricity to electrocute Einstein. If one comes before the other, there's not enough, and Einstein gets to live. Okay, so that's how we're going to do it. Okay, I hope you follow me. Okay, here it is. We're going to put Einstein in the electric chair. Train comes around, sends the lightning bolts, and if they come at the same time, boy, he's going to be carbonized. Okay. On the other hand, if one comes before the other, well, then he won't be carbonized. Okay, so this is an objective test. Okay, we don't need Einstein's opinion. We don't need calculations. It's physical. If the two electrodes are, or whatever we've got there, you know, devices, are struck at the same time, physically, you know, the two currents come and the two currents add up and they electrocute the guy sitting in the chair. We're done. It's simultaneous because there's no other way that the guy would be electrocuted. If one comes before the other, he is not electrocuted. Very simple. No calculations, no math, no opinions, no observers. All we need is objectivity. Okay? And so I like my test a little better because it's objective. His is dependent on what the observer perceived, which is what mathematical physics had been doing for 100 years, just opinions. what this guy had perceived, what the other guy had perceived, and here's the calculation. We don't care about any of that. We need to know physically what happened. Okay, so one of the things that Al-Khalili says is that there's been two confirmations at least. Well, there's been confirmations of special relativity. One of them is the Ives Stilwell experiment, which was done in 1938. It was really a thought experiment done, originally created or generated or imagined by Einstein himself. Okay, and he suggested this experiment. It was actually carried out 30 years later, 1938. That's the first one. The second one is the Muon, which came 2 years later, 1940. Okay, and here's the Stilwell experiment. Okay, it looks more or less like this. I hope you can follow me. Okay, I'll try to go slow here so that you can understand what's happening here. We're going to ionize some hydrogen. Okay, that means we're going to remove the electrons from the hydrogen atom. We're going to leave only the protons. Okay, so the ionized hydrogen is maybe in a canister, so it's just sitting there, it's not moving. It's just, you could say it's a static ionized hydrogen in the sense that the whole blob does not move. But the protons are channeled through and accelerated through the beamline, okay? And somewhere down the road, they're going to be recombined. In other words, an electron is going to be added to these hydrogen atoms, or better, to these protons, and they're going to turn back into hydrogen atoms. We're going to have a recombination, but this atom is now traveling at a high speed. Whereas the ionized hydrogen atoms are static, essentially they're in the same region. These other atoms, because they have this momentum, the protons were accelerated at great speeds. They recombine, but they're still going fast. So these atoms are traveling very fast. Okay, this is the Ives Stilwell experiment. Okay, and so what are they going to do? Well, they're going to compare the stationary wave of the ionized hydrogen atom versus the Doppler shifted wave of the moving wave. Okay, that's in this recombination atom. Okay, these are being accelerated. They move forward. What they're going to be comparing is the forward waves. Remember the Doppler shift, you're squashing the waves in front, and and the waves behind are getting farther and farther behind. That's for sound, it's easy to understand. When the ambulance comes towards you, you have this high pitch, and when it leaves, it has this low pitch. And that's the red shifted sound, you could say, and the one coming towards you is the blue shifted sound. Okay, and we're going to apply this to light. What they're going to be doing is they're going to squash the waves in front as this atom moves towards the detector, and the forward waves are going to be blue shifted, whereas the backward waves are going to be red shifted. They're going to compare it because the backward waves are going to be reflected off a concave mirror, and they go to the detector as well. So we're going to receive both the forward waves, the backward waves at the detector, and we're going to compare the center points. You can see there compare the center of Doppler shift in green, and on the right hand side you see what they're doing. They're comparing the center of these two waves. They're going to be shifted, but then there's the classical shift, what's calculated according to classical mechanics. And if that square, green square on the right, is further to the right, then it means it has time dilated, because it's got this special relativistic effect where it's no longer just the classical calculation, but there's an added calculation based on that factor that I just mentioned a little while ago, the Lorentz factor. So you have to factor that into this calculation. So what happens is how much it's shifted rightwards, that square where the two waves are being compared, the one on the top and the one on the bottom. If that's shifted towards the right, then you have a time dilation. Okay, you have a little bit of time dilation. That's how they came up with this Stilwell experiment, Ives Stilwell experiment. What's the problem? There's a couple problems. And I'm not going to go in great detail over this Ives Stilwell experiment. I just want to mention a couple things. The first one is that Ives and Stilwell didn't believe in time dilation. With their experiment, Ives worked for IBM, by the way, so he had all the toys there to play with. He tried to prove special relativity wrong, irrational. And what he said, no, he believed in the ether. And so he showed, or he thought he showed with his experiment and his paper in 1938, he thought he showed the existence of the ether and the debunking of special relativity. So he had a different opinion than what everybody else concluded from his experiment, which is today used as one of the proofs, one of the confirmations of special relativity. And the other thing I want to mention here is here's a paper and a guy who analyzed in quite a bit of detail. He's got a couple papers out there, and you can look him up, okay? And he says the following, and it's a comparison how they kind of cheat in mathematical physics is the fact that whenever they need the wave, they use the wave, and whenever they need the particle, they use the particle, and whether that's a fair, way of dealing with these issues. The fact that the wave theory of light can describe one aspect of these phenomena, the Ives Stilwell type experiments, cannot overshadow two issues. The corpuscular theory of light, firstly applied to the Doppler effect for photons by Schrödinger in 1922, is by far more complete. The wave theory can be used only when the number of photons at work is statistically significant. The disregard of basic methodological criteria may appear as a minor fault. However, the historical development of quantum physics shows that the predominance of the wave theory of radiation beyond its natural application domain has hampered the reorientation toward the photon description of the underlying phenomena. Yeah, see, so, and I read another paper out there. I'm not going to put all these papers, I read a couple really out there, and they don't agree that this proves special relativity for different reasons. And you should, if you're interested in debunking the Ives Stilwell experiment as a confirmation of relativity, it would behoove you to read some of those papers because they do show that, or at least they argue, very intelligent actually, even though I don't agree with every facet of what they say there, they do argue that it does not confirm relativity, special relativity. And that's what you'll find like in the Wikipedia, all that. They'll mention this Ives Stilwell experiment as proof of special, it's been confirmed, ratified, rubber stamped. Not everybody agrees. And if you just want to understand, well, then you should read those papers. Okay. Anyways, that was one. He had a couple, this fellow. Another experiment came 2 years later, and that was the Muon. Okay. And here's the argument there. Okay. And the one on the right is my picture, but the one on the left is the Wikipedia explanation of the muon. The muon is an unstable subatomic particle with a mean life of 2.2 microseconds, much longer than many other subatomic particles. So it's got a very short lifespan, okay? That's what they're saying. Like I say in the picture, it should decay up in the atmosphere and it makes it all the way to sea level. And if it makes it all the way to sea level, how can that be if the muon only has 2.2 microseconds, since the pion decays and creates it? In other words, the muon is a debris of the pion. So the pions come close to the atmosphere, they disintegrate, okay? And from there you have this muon being born, and it only has a lifetime of 2.2 microseconds from that point on. The issue is that muons have been, according to quantum mechanics, been detected very high up in the atmosphere, okay? And what happens when, it should decay much earlier than reaching sea level. And nevertheless, they detect the muons at sea level and they say, how can that be? And that's when they introduce special relativity. So here's the explanation. It says, muons from high energy cosmic rays generally continue in about the same direction as the original proton at a velocity near the speed of light. Although their lifetime without relativistic effects would allow a half survival distance of only about 456 meters, right? At most, as seen from Earth, the time dilation effect of special relativity from the viewpoint of the Earth allows cosmic ray secondary muons to survive the flight to the Earth's surface, since in the Earth frame, the muons have a longer half-life due to their velocity, okay? Because they travel at the speed of light, essentially. From the viewpoint of the muon, on the other hand, it is the length contraction effect of special relativity which allows this penetration, since in the muon frame its lifetime is unaffected, but the length contraction causes distances through the atmosphere and Earth to be far shorter than these distances in the Earth rest frame. What are they saying? They're saying that the distance has shrunk from the muon's point of view. Okay, so let's see if we understand what they're saying. We have a pion, it's going to disintegrate, and from that is going to be born this so-called muon particle. So now the muon comes down to Earth, except that the muon is born too far up in the air. What is it, 456 meters? That's all it can travel before it should decay, even if it travels at the speed of light. So it should decay far out in space, in the atmosphere, let's say in the stratosphere, okay? Instead, it makes it all the way to sea level. That's where they detect it. So they say, we've detected muons here on Earth. That's what they say, right? So how did it make it? It should have decayed farther up. And so they say, well, from our point of view, it reached the Earth, right? Because there's time dilation. But from the muon's point of view, from its frame of reference, like if it had a little mind there, you know, the distance from the muon to the, or from its birth point to the Earth has shrunk. So it's the distance that has shrunk according to the muon. So everybody's okay. Every observer, every opinion, every witness is okay. Yeah, this witness saw it hit the ground and it shouldn't have, but that's because there was time dilation. That's what this witness said on the stand at the trial. And the other witness says, no, judge, that person's wrong. I'm right. And what happened is really the distance shrunk. And so that's why I reached the Earth so fast. And the judge says, I'm a relativistic judge, and in relativity, everybody is right. No matter what they say, you're all always right. Okay, that's essentially what the status is. Okay, what problems do I have with muon? Okay, well, I try to debunk this nonsense, and here it is. Okay, here's two mountains. Okay, and what happens? What these people are saying that the distance between the mountains shrunk. This is what they're actually saying. Okay, I know you might say, Bill, you're making this up. No, this is what they're saying. Okay. And here's the explanation I give. Relativists claim that because a muon travels at near the speed of light, the distances in its direction of travel shorten. The mathematicians are saying that if a ball travels from one mountain to another at near the speed of light, near C, the mountains come closer to each other because what's shrunk, they say, is the distance, okay, according to the muon. The mathematicians confuse distance with distance travel. That's one issue. The distance of mathematics is a movie of one moving object and is measured with a clock. The distance of physics is a photograph of the gap between two objects, like the two mountains there. The distance of mathematics is conceptually dynamic and requires measurement. The distance of physics is conceptually static and does not even require the presence of an observer. We do not need observers to figure this out, and especially if we're going to, try to figure this out objectively. Okay, so here's the resolution to that. See if you can understand what the problems are with what relativists are saying. Okay, here it is, and here it is. Imagine the universe as a movie. It's the universal movie. Okay. So every action in the universe has a frame. And in that frame, you have location. That's all you have because those are static objects. You have distance and location. You do not have motion within a frame of a film. Okay, so we're talking about cross sections of time here. And there are only two possibilities. either the movie of the traveled portion has more frames, or each frame of the movie represents a greater distance. Okay? Both of them imply that the static distance between the mountains shrunk. If the, let me finish that. If the muon is traveling at the speed of light and is closer to mountain B, then it traveled faster than light from mountain A. And that's another thing you should keep in mind. But here's the issue. Either we have 150 frames of the movie, right? And instead of 100 frames of the movie, we have more frames, okay? Because the muon is closer to mountain B than it should be. So somehow we filled in with more frames of the movie. That means we have more cross sections of time somehow. Or we have the same number of frames, but each one represents a greater distance. So we still have 100 frames, for example, right? But the frames are spaced farther apart than they are, like, in what you would expect. So from the muon's point of view. So the question here is, either way that you look at this, what you're staring at is the mountains are coming closer together. Just because a muon, a little ball, sped between them from one mountain to the other. And so no matter how you twist and turn it, that is the conclusion from a physical point of view. Okay? And then again, the other issue is, if this muon was traveling at the speed of light, and instead of being here, it's over here closer to mountain B, then it traveled faster than the speed of light from mountain A. So no matter how you twist and turn it, you got a problem. You got you're either beating the speed of light, which special relativity has as a principle. Okay, it's fixed. You can't travel faster than the speed of light, at least in special relativity. You can in quantum. We talked about that a couple weeks ago. And the other one is that it brings the two mountains closer together, just because a little ball travels between their two peaks. Okay, so there you have it in a nutshell. So muon is nonsense. No, all these so-called confirmations, proofs of relativity, special relativity, they're nonsense. They're poppycock. It's for people who do math and they say, here, I can show you the equation. I don't care. I don't want to see your equation. I want to talk physics. And if they're going to use this kind of rationale, you can call that, I call it irrational, to state that your twin brother is 50 years older than you simply because he traveled at the speed of light. Well, that's great as an equation, as an exercise. I can play around with the variables, the constants, the numbers. That's great, the little c's. To tell me that's real, that he's 50 years older than, that he's 50 years younger than me, the guy who traveled, right? When the Earth went around the sun, the same for every observer, objectively. All that shows that all that is nonsense. Okay, but that's the kinetic time dilation. That's when you move. There's another time dilation, and people sometimes confuse them. It's important to keep these two separate, okay? One is kinetic time dilation, how fast you travel. The other one has nothing at all to do with speed. It has to do with location, okay? And it has to do with how far away you are from the center of gravity. In the case of the Earth, we're going to take the center of gravity as the exact center of the Earth, even though it's in irregular shape, etc. More or less, it's a sphere, okay? Center of gravity, we'll just pick a point in the center of the Earth, okay, of this sphere. We'll consider it as a perfect sphere. And the clock that is farther away from that point, okay, according to these people, should travel faster, and the clock closer to Earth should travel slower, and the one closer to the Earth should travel faster. That's what they're saying. Okay, so if we have a clock that is at ground level, at sea level, right? That clock should travel faster because the guy traveling out there, because he's traveling near the speed of light, that slows time down according to relativity. That's why the twin that goes into outer space, he doesn't age because time is going slow for him. It's going fast for the guy who remained on Earth. Okay? I know it's a little bit of tangle there. Let me say it one more time just in case. The guy closer to the Earth, his clock goes fast. Why does it go fast? Well, it goes fast with respect to the clock that's up in the sky, up in space. Why? Because the guy in space, he's carrying an atomic clock, and that atomic clock goes slower because of the speed of light, because of the Lorentz factor. Okay, so that's how they calculate it. Okay, so you have this guy traveling at near the speed of light, okay, 0.99% of the speed of light, so his clock runs slower because of the calculation than the guy down on Earth. They said they have proven this. They've proven it with the Haphazardly Keating experiment. They used it. They used a couple experiments to so-called prove this. They always prove. Okay, we proved something else here, and I always show this so that people are aware that not all proofs are proofs, not to everybody, okay? And here's my proof. Wrong one. Let's get the right one. Where is it? Here's the proof, okay? We have two clocks, and we're going to use hourglasses. Hourglasses are clocks, like this one here. Okay. Turn it around, there it is. And what happens, the grains fall to earth, okay, fall downwards, okay. You can see how it goes down, okay. And so what happens, you have two hourglasses there, and the one closer to earth, that one runs fast. It should run faster than the one up in the stratosphere. Okay, why? Because gravity is less strong, it's weaker up there in the stratosphere, and it's stronger down at the bottom. This is a gravitational clock. This clock works only because of gravity. And so here we debunk Einstein's principle, where he says that clocks should travel faster here on, slower here on Earth, and I got that right. I always get that wrong. Clocks should run slower here on Earth and faster. Am I saying that right? The light, the atomic clock on the spaceship, okay, should measure time slower because gravity affects it less, okay? And it turns out that here on Earth, this clock runs faster. And they're saying the opposite. They're saying that clocks here on Earth should run slower than up there in the sky, okay? So we've got a problem because gravity, according to relativity, special relativity, should affect the clock. And if it affects the clock, here we have the perfect clock to measure time. And that is that clocks here run faster. Why? Because they're closer to the center of gravity. Period. We're done. So not all clocks, especially gravitational clocks, pendulum clocks, work the way relativity says they should. So that alone should already put a question mark when they make a broad statement, a across-the-board statement that gravity affects all clocks in the same way. It doesn't. So that's the first thing you should keep in mind. Okay, so yeah, he says this thing, which is incredible. He says gravity slows time down. How can a concept slow down another concept? You got to identify the physical objects. You got to show me physically how it slows time down, not just state it and say, well, we measured it and it slows time down. No, if you're going to talk about slowing down, like physically slowing something down, like you're slowing down a car, you got to put some physical objects. Here I put a hand for gravity. Time, I don't know what I'm going to put. A clock? I don't know. So he says gravity slows time down literally. So if you can find a strong gravitational field and go and live there for a while, slow your time down and come back to Earth, you will also reach the future. You're going to be in the future, okay? This isn't just science fiction. Look what they say. This isn't just some theoretical idea that some genius came up with 100 years ago. Well, if he came up with this nonsense, he wasn't a genius, right? It's been tested many, many times in laboratories that work. Okay, so it's a lot of authority, a lot of concepts, stopping concepts, slowing down concepts, and we still have no physical object in front of us. We don't know what they're talking about because they can't illustrate the mechanism of how gravity concept slows down time, another concept. It's like mass. How does mass pull on a star? Well, we don't know because mass is not a physical object. Here we have something similar. We have gravity stopping or slowing down time, both of which are concepts. So how does it grabs it by the seconds, grabs it by the minutes and slows it down? I mean, these are mathematical calculations which they're introducing into physics without any justification whatsoever. So what does Al-Khalili say? Well, he says if you want um, your clock to change its speed, all you got to do is lift your arm. Okay, he says if my watch is running slow, I could raise my arm and make my watch go faster. Okay, so he's saying clocks run faster up there when I just showed that if it's closer to gravity, the sand clock, the hourglass, runs faster. So we got a problem because what he's saying there is not applicable to all clocks. And why is he going to accept his clock over my clock? Well, we've had all kinds of clocks throughout history. They're all clocks. They all measure time in one way or another. And they're pretty accurate. I mean, you can use an hourglass, like a minute glass, to bake an egg, fry an egg, right? So it works. Okay, I say I could raise my arm and make my watch go faster because it's maybe a meter or so further away from the Earth. It will feel slightly weaker gravitational pull. Yeah, again, sand clock, hourglass. So if gravity is weaker, time can speed up. Absolutely not. If gravity is weaker, time can speed up. Why? It's grabbing it by the minutes, by the hours, by the years. This makes no sense. Ask him to put that in physical terms so that you'll understand it. Tell him to make a picture, a movie of it. Then we'll understand it. But as long as he makes a statement there that is unjustified, I mean, he can say anything he wants. He can say also spirits travel around the earth. Okay, yeah, so here, closer to ground, gravity is stronger. Raise my arm and I can speed time up. These effects can now actually be measured in experiments. So they measure and they don't know what they're measuring. Are they measuring time? What is time? Did you define time? They didn't define time, but they claim that they measured and proved it by running experiments on time. How gravity warps time or slows it down or whatever, or speeds it up depending on how far away you are from it. Where do we have any physical object? What's slowing down? What's speeding up? I need to know what's traveling. Okay, so don't tell me time. Tell me what's happening to the object. Okay, then we'll understand. Okay, so what does Al-Khalili move to next? Well, he likes everybody dreams of traveling to the past and to the future. Okay, so he's going to travel to the future. He says, can we travel through time into the future? He's got to give us hope because Bill Gates tells you that we're the last humans on Earth. This is it. Once the economy collapses here in the world, that's the end of humans. Okay, nobody will produce food for us. And so money will be no more. You'll have nothing to buy because nobody will produce anything to sell you. No company out there produces food to feed you. They produce food to make money. Once money is no more, they have no incentive to do so. Okay, that's a long story, but can we travel through time into the future? Everybody wants to go to the future, okay? Yes, by slowing time down. That's how you do it, okay? But can we travel into the past? Whoa, okay. Can we go see my grandmother? I want to see her again, okay? That is much more difficult. However, time travel into the past is not ruled out by Einstein's theory of relativity. And remember, this is our best theory of the nature of time. This is the best one, okay, they came up with. It tells us that time travel into the past should in principle be possible. But then they run into this grandfather's paradox. You go back and kill your grandfather, so he died. He wasn't married. He didn't have kids, so you shouldn't be around either. Okay, in this universe. In another universe, we don't know because they have that loophole as well. They go through. They created so much nonsense. It's hard to keep up with them. Okay. What is he talking about? Let's see what's wrong with it. Okay. Here's the block universe. This is what relativists have in mind. You have all those lines. Those are the slices of time. Okay. We have slices of time. And think of those as cross sections of time. So all you find within one of those cross sections, and here's a picture of that, just so you can see what I'm talking about. Okay. Here are these cross sections of time, okay, that make up that block universe. Each cross section, okay, each cross section only has location. It's static. There's nothing there. It's a frame of the universal movie. That's what you're staring at. Each one of those slices there, okay. So what happens? Within one of those slices, all you have is location. What these people are saying is that you move from today to the past or to the future. It really doesn't matter. If you go back to one of those other slices on the left, way back in the past, okay, what should we find? Well, here's what you should find. This is the problem. What you should find is this. You should find that the Earth in the year 2020, which is today, or the solar system, right, has a certain location with respect to every object in the universe, every asteroid, every star, every planet. And I've just taken a single frame, so there's no motion there. All you have on the right-hand side, 2020, is location. It's a single frame of the universal movie. If I want to go to the year 0 of the Christian era, that's 2,000 years ago, well, the Earth was in a different location with respect, to, or vis-a-vis, the other matter in the universe. That means if I want to go back in time, I have to take every asteroid, every atom in the universe back to where it was 2,000 years ago. Man, that's a monster. Can you imagine poor old God trying to do time travel into the past? And same thing into the future. You can go from 0 to 2020 and you got the same situation. You have to go to where every star in the universe was 2,000 years ago or 2,000 years in the future if you started year 0. Okay? Is this what's happening? Are they saying that when you travel through time, through the time tunnel, through a wormhole, through the time machine, that all the stars and galaxy, every atom in the universe goes back to where it was 2,000 years ago? Does that seem rational to you? They say it's allowed for the laws of physics. I'm not sure what laws. There are no laws of physics. What they're talking about is mathematics. Actually, mathematics, if they extrapolate their equations to physics, then it's mathematics. Because they're saying you can travel, that it's allowed by the so-called laws of physics that you can travel to the past. You can see Napoleon. That means I have to go to the Earth where it was 200 years ago, okay? And all the stars, everything goes back to where it was as well. Poor old God, I mean, his filing cabinet must be burning. I'd hate to see what his computer looks like. I mean, Jesus. It's up to you to believe through authority. Here's a summary. Go to Al-Khalili. Here we go. Summary conclusions. Al-Khalili claims time dilation has been proven. He starts out by saying, hey, don't challenge me because it just means you're an ignoramus. You don't understand what we've already proven. All you have to do is memorize. Time requires memory, okay? Memorize this. Time dilation is a set of patently irrational explanations, physical interpretation. All they have is irrational explanations. It is irrational to affirm that a brother is 50 years older than his twin, or a sister than her twin. Time dilates. It's a concept. Time is not an object. So how can dilate, meaning what? Meaning that an object travels slower or faster? Tell me about that. Don't tell me about time dilating. Tell me what happened to the clock or whatever object. Distance shrinks between two mountains because a particle flies between them. Okay? And time runs slower close to gravity. We showed that, I don't know about time running slower. That's what I got confused earlier. I know that the grains fall faster, and if if falling of grains is a measure of time, then time runs faster. Okay, so I don't know where they got this time runs slower when we have clocks such as pendulum clocks and um, hourglasses, sand clocks. You also have knots. You know, they use the knot in in the Navy. Okay, you have all these. They count how many knots, how fast a boat is traveling. You can do it with knots as well. And I've got a thought experiment on that. The twin takes the rope, a rope with him with all these knots. Then he comes back. Then he counts the knots. Hopefully both twins count the same number of knots. And not one says, hey, I counted only one knot and you counted what, 50 knots? No, no, no. If you take a rope and this guy, just taking the rope all the way up there and comes back and he counts the knots like, the beads on a rosary. Well, hopefully the two twins, they count the same number of knots. And why? Because counting is not the same thing as measuring. But these people they're not counting. They're doing measurement. Okay? If you count, that's objective. But when you measure, that's where you have to kill the witness, the testimony, the observer. Okay, Einstein's special relativity has no relation to reality. Absolutely not. All their conclusions have nothing to do with our real world. But people love to fantasize about, traveling to the future, to the past, and they get so, hypnotized by all that nonsense. They get taken away that they fly out into Never Never Land, It would help if relativists defined the word time. I mean, if they defined time, we wouldn't have all these problems. But they start out by not defining time, and they say, let's continue with the discussion, with my dissertation. Okay, a couple questions I have here. I don't think I'll have time for more here. Here we go. Our fan mail here. One fella says, Nikola Tesla was primarily an engineer. Secondary, this is because of the other day I talked about Tesla. Secondarily, a scientist. These two occupations go hand in hand for successful inventions. I don't think so. They not necessarily. And inventions by trial and error. You don't have to be a scientist. You can be a pygmy in the middle of the jungle, and without understanding the nature of things, the mechanisms, you can come up with an invention. A table. Just by trial and error, say, hey, I need to put something on here, so I'm going to put 4 legs, a board. Hey, I'll call it table. There it is. So he invents the table. Did he need any science for that? Did he need to understand gravity or magnetism or the electron? No, absolutely not. In fact, like I showed, and this guy obviously bypassed that. He skipped that. Who was it? Thomas Edison? He knew nothing about electricity. Nothing at all. And what he did was try one thing after another because he was a businessman. He tried to make money. He wanted to get a filament that would last long. So he tried one material after another until he got it right. In fact, his own words, I have not failed. I found 10,000 ways that don't work. Period. We're done. That's technology. So you don't need science to do technology or to do inventions. Tesla is responsible for a plethora of inventions. Yeah, no doubt about that. The question is whether they are inventions. Okay, in 20 years of this rope universe BS, not one product. Yeah, because science is not about making products. That's why, science has nothing to do with technology. Science is about explaining phenomena, rational explanations. Whereas inventing means you made a gadget through trial and error. And so here is the summary for that, essentially. Okay, here it is. Tesla was not a scientist at all. Science, rational explanations. That's what it is. So we have to discard Tesla as a scientist. Science has nothing to do with technology. Technology is by trial and error. Science is explaining. Tesla was a researcher and developer, no doubt there. Okay, whether Tesla was an inventor is a different matter. And I discussed that the other day. An inventor is a guy who comes up with ideas. And I think Tesla did some of that. So I think he was an inventor. But if you just go to the lab and do things and then something comes up because you saw something that you never saw before, well, that's not an inventor. That's really a research and developer. That's all it is. And the rope hypothesis is a new model for explanations, not for invention. So hopefully the rope model, and I'll say it here so that you can hear it really good, the rope model is worthless garbage as far as technology is concerned. We have no use for it in technology. I hope that's clear. We have no need for the rope model in technology. I worked in technology for many years, and I did it just fine with particles because we didn't even use particles. We just had to figure out, things about chemical things, like aluminum, titanium, titanium nitride, silicon, polysilicon. We worked with a lot of chemical elements, okay, acids. We had sulfuric acid, we had HF, very dangerous hydrofluoric acid, never touch that stuff, or 10 to 1, which is a 10 water, 1 hydrofluoric acid. All these acids, all these are chemicals. And we didn't need to really know anything at the atomic level. We didn't need to know, what an electron was. Not to do, and I did semiconductors, high tech, very high tech, cutting edge. Okay? We didn't need to know any of this stuff. So no, you do not need to know an explanation of magnetism, of what the real nature of magnetism is, to make a device, to make a chip, to make a transistor or a diode or whatever. So no, technology and science have nothing to do with each other, and until you define those two terms, you can't even enter the discussion. So begin by defining the terms so that we know what's going through your mind if you think otherwise. Okay, and last question here. One more question. I'll cut it short today. You can't defend your definition of triangle. You won't be able to get away with saying triangles only exist in Euclidean space. Okay, that's because I discussed the other day the fact that triangles are only 2D according to the Greeks. I mean, they're the ones who passed all this stuff first to the Romans and then the Romans to us, right? Today. So yeah, triangle was defined as a two-dimensional plane. All the planes include circles, squares, triangles, etc., right? And somehow they started bending the triangles and calling them triangles. See, we don't do that with circles. We don't do that with squares. When you turn a square into a 3D, you call it a cube. You have a different word for that because the square belongs to 2D and the cube belongs to solids, to 3D. The circle, or you could say the disk, belongs to plane geometry. The sphere belongs to 3D solids. So we have a different word for that. These people want to use the same word triangle, and they say, oh, I bent the triangle. Now I have a triangle that is curved. So what they're saying is they have a 3D triangle, except that the 3D triangle is a very thin sheet of paper. What they did is bend the sheet of paper, which has no thickness, but now it's 3D because if you take a look at that, it's got 3 mutually perpendicular directions, no matter how you twist and turn it. Okay, so we have a 3D triangle. Does it belong to solids? Because the notion people have of solids, like when they talk of spheres and cubes, is that it's 3D, like volume, it occupies all this space. And here you have a single sheet that's just bent over, and they call that a triangle. They continue calling it a triangle, but they don't realize they've got 3D now, and they don't fill it up. They don't fill in that space in the triangle with something. They just leave the sheet and they say triangle. It's a bent triangle. And so what problems does this create? Well, here you see some of the problems, okay? And it also gets a problem with semantics because they talk about triangles when they're not talking really about triangles, okay? And so here it is. Here's the answer. Triangle defined as 2D by the Greeks. Circle, sphere, square, cube, triangle, and what do we call the 3D triangle? Well, we don't know. Maybe we call it a tribar. Who knows? Angles, how do they figure out angles? Well, they extend tangents. That's how they do it. Okay. Squares and circles have no width. Okay. So what is the width of a bent triangle? Well, you may say that the sheet of paper has no width, assuming it's zero dimensional, right? So if we look at it sideways, there's nothing there. Okay, that's different than a circle. A circle you see head on. They never paint the triangle facing directly into it, right? Because that curvature would not, that's all we would see. We would see a curved triangle, and people would say, well, that's not a triangle. The only way you can see this curved triangle is sideways to imagine it floating in space, right? And so how is this thin 3D triangle if it's 3D, right? And let me show you a couple images here. This is known as the rouleau triangle, okay? And this is what they've done. See, if you see that little triangle head on, you would say, well, that's not a triangle. Yeah, it's not a triangle because it's got curved edges. But see, they simply say it's circles that are interlocked, and they create these curved edges, okay, around the triangle, and they call it a rouleau triangle. So we have all these great triangles that the mathematicians have created for who knows what purpose. Do we need this in physics? Probably not. And this is in addition to some of these other triangles I talked about the other day, which are here, you see them. Okay, we got the Lobachevsky saddle triangle, the Riemann spherical triangle. One guy put it on his horse, the other one on his baseball, I guess. Okay, you got the tribar. You could say that's a 3D triangle, right? I mean, you know, if you see a cone sideways or a pyramid sideways, you'd say that's a triangle until you see it from an edge and you say, oh, that's a 3D triangle. Why don't we call those triangles? Okay, so it's this sideways view of the bent triangle that is a problem, because you can only see it in a projection and say, oh, I see it's a bent triangle. If you see it exactly sideways, you know, completely on edge, you won't see anything because it has no thickness. So they have to give you that perspective, that sideways perspective, to show that it's a bent sheet of paper, okay, in one way or another, concave or convex. So yeah, we have a problem because it's just misleading in many ways. They should give it a different name, and they should not call it a triangle. You know, they should, I don't care what name they give it, they could call it X and Y, but those are not triangles. So the fact that the mathematicians since the 19th century who worked on this nonsense created these so-called triangles, yeah, people get confused. And I mean, the mathematicians get confused, not me. I don't get confused, but they get confused because they start using the word triangle, and then they after some time they don't know what they're talking about because they extrapolate all these notions into physics. Okay, they talk about the edges, the angles, all this stuff, and they're not talking maybe about a straight triangle. In fact, they've done even worse. They've curved the dimensions to accommodate stuff like bent triangles. They curved the dimensions. So the dimension, you know, used to be, you know, length, width, and height. They were all straight, perpendicular lines. No longer. Now they have curved dimensions, because if you put the dimension on your globe, the one you have in your home, well, for some reason it bends. It follows the contour. So they invented curved dimensions to accommodate their ridiculous theories. Okay, with that, I'll see you on Wednesday.